Hello, mic test. Hello, mic test.
Hello, hello. नाही. नाही देत ते, घेत नाही. मला गरज नाही आहे त्याची, पण ठीक आहे, एखाद्या वेळेस वाटलं तर म्हणून. सर 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 गरज नाही आहे मला, गरज नाही आहे, पण एखाद्या वेळेस लागलं तर फक्त तोपर्यंत मागून ठेवा. इज इट ओके माय व्हॉल्यूम लेवल? हां हो. बसून बोललं तर चालेल, कंपल्सरी रेकॉर्डिंग करणं काही इशू नाही. ओके, जेव्हा प्रोग्राम एक्झिक्यूट करून दाखवायचे त्यावेळेला मग खाली बस, बाकीचं मी उभं राहून डिलिव्हर करायला बसतो.
I request everyone to please occupy front seats, sir. Occupy front seats, everyone, please.
तुम्ही मागून
Settle
जा.
down. We are already delayed.
हॅलो
तुम्ही पण जायचं का? हो हो चालतं.
Guys, settle down fast. आदित्य, वहाँ जाके प्लीज कर दीजिए उनके हेल्प. We'll start.
उधर से भी पैक.
आदित्य हे तिकडे जाऊ. चलो, let's start. I know I'm standing in between you and a next speaker or next valuable session, but let me take this privilege to introduce our next speaker, Dr. Amit Joshi from COEP, Pune. Sir is working as assistant professor in Department of Computer Science and Engineering, COIP Technology, since from 2009. His total teaching experience is 16 plus years and research experience is 9 years. Sir has guided more than 70 plus undergraduate projects, 50 plus postgraduate projects. He teaches different core and elective subjects to undergraduate and postgraduate level. Sir is a senior member of IEEE, member of ACM. He is a lifelong member of Computer Society of India and Indian Society of Technical Education, IST. May I now request Dr. Sudhir Dage sir to welcome sir with the flower bouquet.
Thank you, sir. Yes, thanks a lot. Thanks a lot.
Thank you, sir. So once again, welcome you at S.P.I.T.
Yeah.
And now I am handing over session to you.
Yeah,
Thank you, sir.
So, good afternoon. I know the energy level is too less. Pre-lunch, post-lunch, both. It's very difficult to catch hold of your concentration, but it's my task, whatever is assigned to deliver up to a certain level, whatever I can. So, my name is Amit Joshi. I'm working with COIP Technological University since 2009 in the department of CSE. This is about me. I completed my PhD from Department of CSE, National Institute of Technology, Tiruchirappalli, under QIP scheme of AICT. My area of interest include parallel and distributed computing, GPU computing. You can view my publications on Google Scholar link. So currently I'm with status 5 ongoing PG candidates, 10 plus completed PG candidates, 2 are pursuing PhD. The senior membership, ACM membership and life memberships of CSI IIT, and the recent activity include I successfully coordinated AICT sponsored quality improvement program, post-graduation certificate program for non-CSE teachers of engineering institutions to teach them high performance computing or the particular programming basics of computing and deal with performance aspects. So we will be looking towards the particular part of understanding performance. What do we mean? So may I ask how many of you are belonging to non-CSE background? तुम्ही सगळे बसून घ्या, please. Have a seat. Okay, you are from? Okay, electronics, but allied. You might have studied something related to architecture or organization. Mechanical. So allied. E and C. Okay. So rest all are from CSE. So CSE guys might have learned about the particular part of computer organization in their degrees, and that too being very precise, theory course. Cache hits, misses, DMs, input outputs, PCI, PCI, that's it. No out of order, only in order, or whatever is teacher teaching, let us get acquired, whatever is there, digested, that is ours, rest, swaha. So as sir told, in continuation with Sulabh or Sulabhata, madam, I prepared my own poha recipe. I added all essences in it. It is up to you whether you like it or not. But my inner satisfaction is up to the mark. I am fully satisfied. With that confidence, I came here. Because sir told some time back, you need to change your way of assessment. That has been already changed 6 years back when I came back from QIP. So the thing is that we need to, sir uttered one more, your daira is up to your subject. So what you can innovate, you need to just give somewhere out of the box. So take some time for yourself, so things will automatically come outside as a different way. Whatever I will be teaching to you that I learned 6 to 7 years back at IIT Kanpur in a summer school of computer architecture. Then I added those all contents in my curriculum. I executed these in my compulsory subject. Then it came to elective subject because AIML boom, that bubble, big bubble come up. Though nobody is interested to look towards the particular part of systems track, being very sincere. And next thing, okay, we are there with AI, ML, data science, whatever it may be buzzwords, but people just used to forget every time until unless computing is there, nothing is there. So everything comes to computing. And when then there is a need to analyze, you need to somewhere take the quantitative approach to deal with the things, what exactly your system is behaving whenever you are doing something. Whether with respect to the hardware parameters, events, with respect to the particular part you are doing in your programming and so on. So sky is the limit. The particular contents are introduction, performance and execution time, instruction, CPI, statistical analysis, measures of matrix, misuse of matrix, geometric harmonic mean. No need to teach very much explicitly. We are all engineering teachers. Mean of a ratio, what we can deal with, that we need to just see because resources or sharing of resources is involved in our system. Program optimization, references, this is part 1. I will start up with part 2 also, and something is new. I am sure you will learn some new stuff over here and practice with going back your students so that it will give you another level of satisfaction. Everything is open source and the contents whichever are designed through the program, through the particular installations are available in a lab self-explanatory manual that will be provided to you. Don't worry, don't take photographs, everything is there. The stuff will be given. It is open, you can modify and just continue with. So what do we have in a great 8 ideas of computer architecture?
शूट करते हैं ना लाइव स्ट्रीमिंग तर हे पीपीटी होती ते व्यवस्थित करणे याचं कॅच होत नाही तर तुम्ही शेअर करू शकता
आता लगेच हो देऊ शकतो काही प्रॉब्लेम नाही.
मेल करा
तुम्ही पेनड्राईव्हमध्येच घेऊन टाका ना, परत अनदर डिले होईल आपण अदरवाईज. So shall I continue or what? So we have 8 ideas in computer architecture. Recent generation processors, we could able to see whatever we just use at our time. Intel Pentium was a dominant thing. Okay, P3, P4, whatever it is, and it was just a single cycle implementation somewhere. Somewhere it might came into superscalar, but without hardware-based multi-threading approach. And what we can say, it is having a the particular conventional uniprocessor. So when we say I have a design for Moore's law, already it is dead because we are not following the thing that every roughly 18 months or 2 years the particular transistor capacity getting doubled. Instead of that, what is happening, sir? We are trying, rather than we say the architects or hardware designers are trying, those who are belonging to ENTC people. So those who are just planning, rather than doubling it per 18 months or 2 years, we are trying to dump or double number of cores. The cores are nothing but 2002 onwards, the particular core architecture part came into existence, and thereafter onwards, as the particular process is changing. So now we have the process of 9nm, 7nm and so on. Might be rather less than that. Okay. So OnePlus, my handheld device is having 9nm process. So recent generation AMD or Intel, you take 7nm process. So as the particular model followed by Intel, TikTok model, in a 2 cycle of one particular phase, one is a tick, 1 year is a tick, another year is a talk. So in tick, your microarchitecture changes, your talk process changes. So what we are doing, we are having the doubling number of cores. That is the thing. This is already dead, but it is somewhat modified to multi-core era, where we are duplicating the compute resources. And I hope some sessions happen with respect to multi-core and many-core. I don't know, in sequence. So in multi-core, when I say the particular number of cores are limited and hence the number of threads are limited, what will happen, sir? That particular host or processor is emphasized to do tasks, and it is morely dealing with latency. It is morely dealing with latency. In contrast, when I say I have a many core, graphics card, GPU, any particular microarchitecture, taking from say Fermi to till Hoffer, Ampere Hoffer and Lovelace is upcoming, or somewhere it is in R&D lab. So whichever is there, that all are dealing with multiple number of threads for throughput. So that kind of cores are throughput oriented cores. So we are just dealing with this, and we have a combination of both of these, saying heterogeneous system architecture, HSA. So every one of you, until and unless the graphics card is not there on board, or we explicitly don't ask for that, everybody is having the particular heterogeneous system architecture.
वरती बाजूला आहे ना,
काय
त्याच्यावरती तिथे क्लिक करा. हां, इथे
ॲक्सेस
हे काय कुठली घ्यायची, 12 वाली घ्यायची की 1?
1 वाली, आता 1 चालू आहे. Then we have some abstraction. We are not giving every detail whenever we are just changing the microarchitecture, but we are adding up the features. Like once upon time it was in order processor, then it came into multiple issue, out of order, then added the branch prediction logic and so on. Then next to that, making common case faster with minimized power consumption or energy consumption and one particular better level performance, just decreasing execution time, taking a Gödel meter of this. We just took making common case faster, another idea. Next is performance via parallelism. So parallelism exists both in hardware and software. So those who learn computer organization in their basic course of UG, PG, whatever it may be. So what is the particular parallelism that exists in your hardware or architecture? May I ask? Which is the way that you learn, that you say, sir, this is a parallelism in my architecture or in my hardware? I am saying architecture. Yes, that is the next thing. So what we do in process of pipelining, we allow the execution of set of instructions or bunch of instructions in overlapped manner. That will increase the throughput of that bunch of instructions, not a single. So it is directly proportional to the particular number of stages, K, in short. So I have the performance via parallelism both in hardware and software. Hardware, the process of pipelining. Again, it is not a simple pipeline, it is a super pipeline, 1.5 issue per clock cycle, or extension to that or new version of that, super scalar processor. So we have such multiple pipelines acting upon per cycle. That is another concept. Another way of performance via parallelism is nothing but you are explicitly writing parallel codes For example, sir will be taking for you the OpenMP part. How the loop-based parallelism can be achieved. How for a for loop-based identified part, you can just independently execute each and every iteration of that particular for loop. Plus, how you can say to the compiler, yes, I am just willing to use the hash pragma based clauses over there, and this need to be executed in parallel way, like the parallelism in software, performance via prediction. So whenever we use a simple predictor scheme, there was no predictor scheme. First of all, pipeline used to be flushed, because if it is not going to a better or needed effective address of the target instruction, then everything will be waste. So then came into picture. So it is deteriorating somewhere control hazards. So how many types of hazards we observed? That obstacles the process of pipeline, data hazards, raw, war, wow. Second one is structure hazard, that is limited due to the set of resources. Third one, control hazards, that are also known as branch hazards. So if branch decision is not coming into picture in a better sense, we need to flush the pipeline. Then came into the need, into the picture, the need of predictor. So whichever level of predictors you are taking into design, a simple 2-bit taken, previously taken, next not taken. Likewise something that we came to a multi-level predictor, then a combination of global and local predictor, and nowadays we have in Intel Core i7 tournament predictor. That is a combination of multiple things. So it has a multiplexer to select what is the particular statistics. We used to have a branch prediction logic. Depending upon the history, what the particular branch has behaved, and that we are storing in a table, that will be giving a kind of prediction. And how much is the success of the predictor, sir, is nothing but it is depending upon how much accurately it is predicting the branch. That is nothing but its accuracy. So that is the next thing. Last but one, hierarchy of memory. So earlier, before 386 or up to, say, roughly, what was off-chip cache component was present. There is no off-chip cache component nowadays processor architecture. Whatever cache subsystem is there entirely resides on chip. What is your off-chip component of memory? That is in board, only your RAM. And next to that, out of the board, everything secondary, optical, magnetic, tape drives and so on. So how the particular hierarchy of memories you maintain. So multi-level cache design is one of the way to just achieve another level. So all these particular, the final one, dependency via dependability via redundancy. So we could have like RAID, mirroring, the simplest way. So we have some redundancy and we can increase the particular. So the availability is one of the major concern. So these are the ideas that certainly gives an impact directly or indirectly on the performance of our computer system. So why we are having, sir, do we have everything in now present generation processor? Yes, we have everything, sir. We have everything. So the thought process is driven likewise. So you can see a simple example. I have a passenger capacity for airplane and I have a cruising range in miles. Then I have a cruising speed miles per hour, and finally I am taking a product of passengers and miles per hour. This. So maximum capacity of passengers and maximum miles per hour traveling speed, whatever is there, that is outperforming. So which is outperforming? 747 as a combination of both of these. Okay, so we can understand in very general sense. Now when it comes to our own part, when our computer system is concerned, we have a certain, what you can say, performance matrix. So one is response time, how long it takes to do a particular task. Precisely when our processor or host is concerned, what is a multi-core, it is just dealing with doing tasks. Just dealing with doing tasks. So how it is just dealing with the doing task is nothing but it is morely related to minimizing the latency part. Means in a one particular clock cycle, the demand is kept, and in particular clock cycle, the demand is satisfied. In between how many number of clock cycles we are wasting is nothing but you are roughly the missing part. So that is the latency. How to minimize that? For example, in very generic sense, when we are just studying, I have Shall I rub this one? So when I have this quad core processor, for example. For each core, I have a scenario L1, D and I, that is a split but private cache. Again L2, this is unified private cache to each physical core, and this is the L3. This is the last level cache, but it is shared among set of cores. So this is your chip boundary, and whatever is there of chip in board component is nothing but your RAM. So what we used to do, sir, whenever a processor, this is your independent processor, duplicated compute unit, physical core. Okay, in hardware based multi-threading, each particular physical core is supported by 2 hardware threads of implementation that acts as, each one of that acts as a logical CPU, independent. On top of this or using this, you can do anything. Multi-threading, your P threads, your Java-based things, Java-based threads, you can do anything. So 2 hardware threads of implementation, where we can observe. So if I have a quad core, so 4 into 2, how many? We have 8 logical CPUs. Go to Ubuntu system monitor, you will be able to see this. This is in Intel or AMD's context, which follows x86 base. Okay, x86 base, CISC style of, what we can say. Nothing is pure. Don't ask me, sir, whether it is a pure CISC or pure RISC. Nothing is pure or impure. Okay, CISC, internally it converts into RISC kind of things only. Small, what we can say, set of instructions. But when I say it is so, I can just do a lot because we are duplicating the compute units. This is in case of AMD Intel. If you go another way, some way a physical core might be supporting, instead of 2, 4 hardware threads of implementation. So 4 4s are 16 logical CPUs and so on. So find out reading assignment, what is that? So when I say a physical core is in need of some data, once we move from bottom to top, the data transfer unit changes. Pages, block, 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 from block to word demanding core or processor. So when I say certainly one particular word containing block is not available in L1 data cache, that means L1 miss happens. For sure it will have alongside TLB lookout, and if that TLB is hit, then naturally the request will be forwarded to L2. It is miss, hit, it will provide. If it is miss, again side by TLB lookout. If TLB is hit, give here, and if it is hit provided, if it is miss, the request will go off chip component. The dash thing is your chip boundary. So when I say the cycle in which the request has been kept and a cycle in which the request is satisfied, what will happen, sir? We'll lapse some number of cycles in between, for sure, because L1 data is the closest one here. At that moment, what we are supposed to do, less number of clock cycles will be wasted. That is your miss penalty. How do you calculate? When a particular required word containing block is not available in L1 data cache, what happens, sir? That is a miss. That is a miss. And when I say if it is a miss, it need to be serviced. It need to be serviced. So likewise, as I discussed, it will be serviced. Here X number of clock cycles will go. Here X plus some Y clock cycles will go. Here X plus Y plus some Z. And when the particular request will go off chip, then greater than all these number of clock cycles will go. That is your miss penalty. So when I say that miss penalty need to be minimized, that is a kind of latency. So host or processor cores concentrate on that. I don't know what we observed, the control part, the memory part is more when processor cores are considered. The control part. So what we have? ALU. ALU consists of 2 arithmetic logic unit, control, the particular processor, ALU, arithmetic logic unit, control unit. Control unit generates the signal to do certain tasks. Upon receiving the signals, that task will be performed. Hardware based control, microprogram control. So when I say if it is so, then in that case, the particular control part and memory will be more in number when host or processor's chip is considered. When we go to the particular many core, graphics card or GPU, there the control and memory part is less. There your compute part is more. So whichever the area on that particular device is there, the compute part is more. Hence, the number of threads which are generated by your host or processor are very much pretty less than that of your coprocessor or graphics card or GPU. There we used to have 1000 to lakhs number of lightweight threads. That threads are also lightweight. So when it is so, I need to minimize this one. Then throughput, total work done per unit time, task, transactions, so on, whatever you calculate. How are response time and throughput affected by replacing the processor with faster version? Just take higher frequency. Just take a higher frequency, adding more number of processors. So what was the call taken by Genesis of multi-core design is nothing but instead of having a 6.0 gigahertz, take half the frequency and duplicate the resources, multiple it. Yeah, that is known as in I think EC DVFS, differential voltage and frequency scaling kind of thing. So that is directly proportional to voltage and frequency. Okay, so what happens? What we are doing with lowering the power consumption, because normal CPUs earlier to core architecture, they used to face three walls: heat or power wall, ILP wall. There is a very small fraction of instruction level parallelism, that is nothing but your pipelining, and third one is nothing but your what we can say memory. So the latency remaining unchanged. So if it is getting faced, just have multiple duplicated resources. Okay, fine. And minimizing the power requirement, keeping frequency same, you believe you are just doubling the performance. If I say it is coming to 1.88, 1.90, 1.9 something, you are almost doubling the performance. So when it is so, it is the particular dominant architectures nowadays, until and unless you see in very much embedded class of architectures of processors, everything you could able to observe is a multi-core. Okay, since 2002. Now, one by one, relative performance, we can define performance is 1 by execution time. Performance, when I say relative performance, X is n times faster than Y. So, I eat one puran poli, okay, and sir eating 4, let us assume. So, it is 4x. So, when I say performance of x divided by performance of y, you put performance of x with this, then it will reverse execution time of y divided by execution time of x, that is nothing but your n. That is the particular relative. So, example, time taken to run a program 10 seconds on machine A, 15 seconds on machine B. The execution time of B by A, 15 by 10 is 1.5. So, A is 1.5 times faster than B. Relative performance, relative measure. Now, when I say if it is so, very basic thing. Next we can go with a speed up part. So, how one is related to another one? That this example I will be showing through programs at the end of today's session after lunch. Don't worry. So, now we will not keep our mind in program. So, what is written, sir? We are not getting the thing. It's very difficult. You have your food. Be with a cool mind. We will just see how this is getting done. Because we are doing the same matrix multiply by using your host CPU and by using your GPU. Both. Either say 1000 by 1000 capacity, 5000 by 5000 capacity, and so on. So, when I say a speed up, that quantifies the performance gain obtained by enhancing a system or component. It is defined as a ratio of execution time before the improvement to the execution time after the improvement. So, whenever I say speed up, it is equal to execution time of older version to the newer one. Makes sense? So, I will get back to this point through one good example. A computational task take 20 seconds on a CPU. After transitioning to a GPU system, the task completes in 5 seconds. So, speed up is of 4. So, the GPU based system performs the task 4 times faster than the original CPU or host based implementation. Measuring execution time, we can see elapsed time and CPU time. Elapsed time is a total response time including all aspects like processing, I/O, operating system overhead, idle time. It determines system performance as of the entire one entity. But when I say it is a CPU time, we have two types. One is your time spent processing the given job, discounts I/O time and other job shares. It comprises using CPU time and system CPU time, user CPU and system CPU, and different programs are affected differently by CPU and system performance. So which are those factors? We will come back and see shortly. This is the clock, no need to share. We can just take it a conversion of this. So 250 picosecond, 0.25 nanosecond, just conversion. So now with gigahertz, something, some dot some, 3.0, 3.2, some gigahertz, the particular clock frequency or speed you can say. Now here comes into picture a part of the CPU time. So CPU time we just discuss with the number of clock cycles and a clock cycle time. So when I say a particular CPU time, the particular number of clock cycles that are needed to execute a certain program, instructions, set of instructions, multiplied by clock cycle time. What exactly one particular clock cycle time is taking to complete the clock. And this particular clock cycle time is replaced by your clock rate. That is nothing but 1 by f. So when I say the execution time has to be written, this is known as processor performance equation, n into CPI into T. And this T can be replaced by n into CPI by f. That f is nothing but your clock rate. Makes sense, sir? Now when I say alternatively when book changes, so as sir told, we came from foreign authors to Indian authors to local authors to university authors, now branch authors, the coming part as per the GPT. So when I say this is instruction count, IC, either n into CPI into T or IC into CPI to T, one and the same. So capital N stands for the total number of instructions, IC instruction count. You can alternatively find this one. So performance again improved by either you reduce the number of clock cycles that are getting for one particular set of instructions, or you increase the clock rate as I told, but just increasing clock rate is not solution, because if you are going with the uniprocessor design, what it gives is nothing but the three walls, heat wall or power wall, then ILP wall, memory wall. Now we are out of the box, no issues, but still it is not suggested. Hardware designers or architects must often trade off between clock rate and the particular set of cycle count. Now we can take one example of this one, how to calculate CPI. So computer A is dancing at 2 gigahertz, 10 second CPU time. We are just putting one target of computer B, aim for 6 second CPU time. 6 second CPU time. It can do faster clock, but it causes 1.2 times number of clock cycles. So now, what is the question? How much fast must a computer be clock rate? So when I say clock rate of B, this is already just discussed, CPU time. CPU time we are bringing here, clock cycles of B divided by CPU time of B. 1.2 into clock cycles of A. Yes, we can just go with a faster clock, provided condition, it causes 1.2 times clock cycles. So put it here as it is. 6 seconds is a CPU time of the particular machine B. Now just calculate for A, clock cycles for A, CPU time of A into clock rate of A. So what is that? 10 seconds into 2 gigahertz. So 20 into 10 raised to 9. Giga stands for 10 raised to 9. Now if it is so, clock rate of B, you put this thing as it is in the above equation. So 1.2 into 20 into 10 raised to 9 divided by 6 seconds. Calculate this, you will get one particular figure. So while aiming for 6 seconds CPU time, what is that, sir? 6 second CPU time, your processor B must dance at rate 4 gigahertz. Okay. Now this is one aspect we can just deal. Another, as I told, this one, instruction count into cycles per instruction, instruction count into CPI into clock cycle time. What I wrote, N into CPI into time T, or IC into CPI into T. This T can be replaced with your clock rate frequency again. So instruction count for a program is determined by your instruction set architecture, your program, how you are writing, which language you are preferring, how many instructions are getting after compiling, and the compiler technology, which compiler it is there. Actually, hand in hand, whenever architecture is or processor development is involved, architecture and compiler development goes simultaneously. So the thing, one, average cycles per instruction. Average cycles per instruction that are determined by your CPU hardware architecture, how much it is taking. In different instructions have different CPI, then average CPI is affected by instruction mix. So I will come back to that point in coming slide. So when I say this is the stuff, computer A cycle time 250 picosecond, CPI 2.0. Computer B cycle time 500 picosecond, CPI 1.2. Both are of same instruction set architecture. Both are using same. What happens? Which is faster and by how much? So we can just take again the relative performance. Yes, this you put as it is. I you put as it is, or IC you put as it is. N you put as it is. Is it given? No. Whenever relative performance is to be taken, you can just cancel it, and whatever is coming into picture you can just giving as it is. I will stand cancel 600 by 500 picosecond 1.2. So A is faster than 1.2 times with as comparison with B. So that is another one. Now the cycles per instruction. So we have all particular set of instructions or different types, sir? Yes or no? Or all are branches, all are adders, all are multipliers, or all are divides? We have an instruction mix. Okay? So we need to calculate the effective CPI. So how to? First of all, so in different instruction classes take different number of cycles. So if add is taking 2 number of clock cycles, not necessarily divide must take the same, if it is somewhat complex to perform. So when it is so, then we have in a program average of that one. So instruction mix that will be affected by the different number of clock cycles that are getting consumed by different instructions. So summation of CPI of I into instruction count from I is equal to 1 to n, this is the weighted average. So CPI is equal to clock cycles divided by instruction count. So this is again summation of CPI I multiplied by instruction count I and the total instruction count from I is equal to 1 to n. So whatever this ratio you could observe is nothing but your relative frequency. So you can calculate likewise. One example on this. So don't write anything. I will be giving these PPTs and the course material. It is already in PDF format with me. Alternative compile code sequences using instructions in classes A, B, C. What it does, sir? CPI, this table represents CPI and instruction count. Okay, fine. CPI for class A, B, C, 1, 2, 3 respectively. Instruction in sequence of type A 2, type B 1, C 2, and instruction sequence 2 this one. So for both the instruction sequences 1 and 2, calculate CPI, effective average, whatever you say. So when I say it has to be there, total instruction count for sequence 1, sir, 2, 2, 1, 5. Now, how the clock cycles are there? 2 into 1, 1 into 2 plus 2 into 3. Likewise, if you calculate, it will give you the weighted average, whatever we have seen in the last slide. And if you do this, it will come to 10. And when I am supposed to do the average CPI for this instruction sequence, 10 by 5, the total number of instructions, the average CPI will be 2.0. Likewise, I have the same sequence 2, 4, 1, 1, 6. The instruction count is 6. 4 into 1, 1 into 2, and 1 into 3, 9. 9 divided by 6, 1.5. What is your average or effective CPI? 1.5. So how do we calculate to just go ahead with the particular part of this one? So this is the big picture. We can say CPU time, instructions per program, multiplied by clock cycles per instruction. It is again affected by the different clock cycles that are getting consumed by different set of instructions. Hence, the CPI will, average CPI will just get differentiated. And finally, seconds per clock cycle. How many seconds each clock cycle particularly is taking. Now, this is one thing. Now, entire performance is depends on algorithm design that affects instruction count. It is totally responsible for your instruction count, possibly CPI. So how much effective design of algorithm you are doing, that much minimum number of instructions will come into picture. Okay, so we have multiple approaches. We studied in our basic algorithm course, and we have parallel algorithm course design also. So in that you can just take and attempt to have a divide and conquer kind of thing, to just do it in a parallel way using either OpenMP or MPI or CUDA, something. CUDA, C-based CUDA or PyCUDA, something. Next, programming language, it affects IC and CPI. How effective it has been created, how effective the particular features of the programming languages are given, it's totally depending on that one. Compiler affects instruction count and CPI, both. Instruction set architecture, whatever you are designing the set of instructions, that affects IC, CPI and the particular T. So this is the whole and soul big picture. Now summarizing the data by single number, this you all know, no need to teach. So indices of central tendencies, mean, median, mode, you know, but when to use what is another stuff. So these are the particular diagrams when I say the thing is there and the particular what you can say, somewhere the condition mean and median both are existing, but it might be the condition in some cases there will be no mode. So likewise the thing is there or scenario. So in a flow, if your data is categorical, then use mode. If it is no, if it is of the total interest, then use mean. Again, if both the conditions are not there, if it is a distribution that is getting skewed, then use again median. If nothing is there following, just use a mean. Likewise, the concept is. Now, there are multiple things whenever misuses of the particular indices are there. So when I say using mean of significantly different values, 10 plus 1000 by 2, 505. So mean a typical system A and B, and when we are summing up with system A, B, the mean is 10, the typical is 10 and 5. Likewise, so using mean without regard to the skewness of distribution, then multiplying mean of product E of xy is not equal to E of x into E of y. So in a time sharing system, whenever OS is concerned, average number of users 23, sub processes 2. What is the average number of sub processes? 46. It is not. So the number of sub processes a user spawns depending upon how much load it is there on system. So taking the mean of ratio with different bases. So likewise, geometric mean will come into picture when 7 layers of one particular network we just go through. We have the protocol layers 1 to 7 and the performance improvement from the physical to say application. Last, average improvement, we are just taking each one. So 1 over that particular 1.18, 1.13, everything we are multiplying and raised to 1 by 7 minus 1. So it will come to 0.13. Search it out. I'll give some time.
Sometimes it may be happen that we are not using all the variables. And how exactly it is calculated?
That will be skipped, madam, directly. That will not be considered. Then again, examples of multiplicative matrix, cache hit ratios over several levels of caches, miss ratios, then percentage performance improvement between successive versions, error rate. Likewise, the things will happen, and geometric mean, harmonic mean of ratios will be there in picture, and then weighted harmonic mean also. So weighted harmonic mean in case of MIPS rate, that is another measure of performance we just used to have. There is certain formula for calculating that one also. So that is weights are proportional to the size of benchmark. So Wi is equal to Mi divided by M plus M1 plus M2 plus again so on up to Mn, and weighted is like this one, x dot dot M1 plus M2 plus and so on divided by T1 plus T2 plus and so on up to Tn. So mean of ratios, again some of the numerators and some of denominators both have physical meaning. The average of the ratio is ratio of averages, and again it is given with the same. So whenever we say mean of ratio, the CPU utilization 1, 1, 1, 1 and 100 measures of the duration, and we are just taking the particular one CPU busy, so it is 200. So the mean is not 200 by 5 or 40%. It is not like that. So instead what we are doing, mean of CPU utilization, sum of CPU busy times and sum of measurement durations, we are just taking the addition. So whenever you are calculating, it is 21%. So ratios cannot always be summarized, okay, by a geometric mean. So geometric mean of utilization is useless. So again the special cases of mean ratios are there. So we have just taken one example of our concern, that is nothing but CPU, because the particular resource sharing is happening in that particular environment. So references for these particular part, computer organization and architecture, RISC-V edition as well as 5th edition of Hennessy Patterson, an art of computer system performance analysis, techniques for experimental design, measurement, simulation and modeling by Raj Jain. That is the chapter 12. So now I would like to move to the particular part of my second presentation. Now this particular part gives you an idea about what we can say, whatever we have learned theoretically, how to observe it practically, sir. As I told, many of we studied the particular part of computer organization. Okay, when a block is not available in particular level of cache, a miss happens. How many such misses? At a stretch, a miss particular rate in percentage or level wise. What is the execution time? How the particular time is varying if I am taking different approaches to write a kind of program. Okay, and how I am just moving from one particular architecture to another one, how the things are getting impacted. So we need to somewhere see the things practically also. So one is the perf introduction. It is the tool that is available in Ubuntu Linux platform, open source. Matrix multiply example, row measure and inversing the particular order or loop inversion, we call somewhere in terminology, column measure approach of the same. Tiling approach, what it gives us, another way of optimization, and finally a rough idea about benchmarking and set of references. So what is perf? Perf is nothing but it stands for performance counters for Linux. Earlier available since 2.6.31 2009, it is a command line tool for CPU performance analysis. It monitors hardware and software events both. So whenever I say cache, it is a hardware. Okay, whenever I say cache, it is a hardware. Rather than that, what we have? Execution time, CPU, user. Okay, rather than that, what do you have again? Something. Rather than if you move off the chip component of the particular memory hierarchy, that is nothing but your main memory or RAM. So what happens? Certainly, if the particular L3 miss happened and the request goes to your main memory, and further in the main memory data is not available. What is the scenario? So what will happen before that? Page fault. Page fault will occur. So whenever a page fault will occur, that required page, if memory space is available, then it will be swapped into your main memory. If space is not available, then the particular page replacement algorithm will be first applied. Not needed page will be written back to the disk, swapped out. Needed page will be swapped in. Agree up to this point? So when I say from secondary storage, we move up to the part of physical processor core, that is a duplicated compute unit. The data transfer units are first secondary storage to primary main memory RAM page, from RAM to your on-chip shared L3, LLC last level cache, block, L2, L1. From L1, they will not give the particular entire blocks. The particular data will be delivered in terms of words. That's why whenever we say we have an address split in any kind of particular address, like directly mapped cache, fully associative cache or set associative cache, the least significant bits are what, sir? Word or byte offsets. So the words are getting delivered. So when I say one particular miss happens for L1 and L2, it will just have a alongside TLB look. If a TLB hit is there, then the request will be forwarded to the next level of cache. But a TLB miss is there. What is that, sir? So what is TLB? TLB is again translation look aside buffer. It is a special type of cache designed, and that is also set associative. But if the miss happens, what is the meaning of these TLB miss? There are two meanings. One meaning is, if a TLB miss occurs, that particular data is not, data entry not available in TLB, one meaning. Another meaning, that TLB entry itself is not modified, though the data is there. So TLB is nothing but your fraction of the page table. It checks whether that particular hit means that page is in main memory. If it is a miss, the page is either not available in main memory or the TLB or page table entry is not updated. So when I say such things are happening, small, that is on chip. Not, that is a subset of your page table. It's not entire. So for example, Intel Core i7 L2 TLB alongside 5 into entries only, compared with your entire page table. Yeah, it is a cache only. That will have a set associative behavior like your normal cache, but it consists of that entries only. That indicates if it is a hit, for example, TLB hit is happening, means that page is available already in the main memory. If it is a miss, we have two meanings. One, the page is not available, or the page is available but the TLB entry is not updated. So any of the two approaches need to be processed. So if I'm going for so, then I need to check what is happening in this context. So when I say page fault is happening, I was on the part of page fault is happening. The page fault is nothing but your software event. Cache misses, hardware event. Instructions, clock cycles, hardware events. Likewise, I am willing to say how my program is behaving in a certain aspect if I am changing of the way of writing my program. That is one concern. So monitors, hardware and software events, key features, system-wide statistical profiling, kernel and user space, CPU performance, monitoring unit, PMU, lightweight with detailed performance insights. Many of the places, like one more is their alternative to that, you might have heard VTune of Intel. That is another way of profiling, doing profiling and the performance analysis. And another one is a PAPI tool, PAPI. So this is the open source that is available in your Ubuntu system. When I say why to use perf? So enable low overhead performance analysis, helps identifying CPU bottlenecks, cache inefficiencies, branch prediction issues, memory access patterns. So this is also, all these things are having indirect or direct impact on your system's performance. When it supports both system-wise and pre-process monitoring, it is useful for performance optimization in HPC computing, system programming and algorithm optimization also. So what is one optimization that is applied, that I will just discuss at the time of discussing tiling approach. Event monitoring, hardware events, software events, CPU performance counters, cycles, cache misses, branch predictions as I told just now. Software, context switches, page faults, CPU migrations and so on. Then trace points, kernel level instrumentation points, the modes of operations that include stat, it count hardware software events during execution. So perf space stat space -e, that we will be using a command that gives you the particular information. Record, create profile data for the later analysis. Report, analyze recorded performance data, and top, the live performance monitoring. So that is, madam, when one particular task, so there is something in multi-core environment, load balancing kind of concept. So if that uses usually the readback tree, the property to balance the load. So certainly if in a queue of one particular physical core, say sake of understanding, one particular physical core, 4 cores are there, quad core system. In one core's queue, there are multiple processes, the load, and one relatively there is less. So they will just balance the thing by migrating it. So RB-tree is a balanced one. So they use in multi-core optimization, I will give you the reference also, you can read it from there. So they use balanced tree to just bring it in an equivalent level. So I would like to show you one more. For example, why do that is needed, or what is the need of that particular optimization. You can see this one, everyone? So this is a system monitor in your Ubuntu. So that shows you the resources. The first itself is a CPU, the particular number of things you can have. So you can observe few things that are closed or on x-axis. Make sense? And some are somewhat slightly above the x-axis. So all are with different colors. This is already available. You can go back and touch up with in Ubuntu. Okay. So whichever are above, for example, yellow, orange, this one and this one. So above the x-axis means the utilization is up to more, better extent. And whichever are near to x-axis comparatively than these both are on the x-axis. What is meaning of that, sir? No utilization. That means what we people are doing. You have a farsan kept beside a poha dish. It is there, but you are not pouring in on it. It remains unutilized. It remains unutilized. The thing is that it is responsibility of programmers or software developers, whatever one particular compute facility or capability is given by your underlying architecture need to be utilized at its better extent. So still when I am saying, sir. Yeah, there are approaches. We can do loop inversion, we can do unrolling. There are multiple approaches that are already there in existence in architecture itself. But when I say, when I am writing the program, still my approach is a sequential. I am not making the resources fully available or capable to just get utilized. So none of the things. So whenever I say, okay, we can say Niagara processor, Sun. So it supports 4 threads, for example, or 8 threads per core. What will be the thing if I have quad core, 4 4s are 16 logical CPUs? What can I do with the 16 logical CPUs, sir? Until unless I am not changing my way of writing the program. So hence the OpenMP and MPI in a distributed environment, OpenMP as a shared memory programming, that gives you some scope. Whenever something is there, how we can run that particular thing in parallel. So whenever writing software, it is very, very important, or programs, to just give a thought process, how I am just dealing with the thing. So whatever underlying architecture gives us. So, okay, forget about this. All of you knew GPUs, you came to learn HPC, insights here. All of you know GPUs. May I ask, why do we need GPUs, sir? Madam? Somebody? Means what? What is the need of GPU? Can't it be done with this because it is underutilized? Huh? Sorry? This is also computing parallelly, madam. Everything is parallel. Already the architectures are parallel architectures. Faster processing. Architecture is? That itself I uttered. Whenever I am just saying, my host, my CPU is there in picture, that cores are designed for minimizing latency. There is something that is known as, in Kai Hong's book, if some of you have referred in your academics, Kai Hong and Naresh Jyothwani, the second, third edition also came in existence. Once upon time, the Kai Hong's older book, like blue color was there, that was too much, what you can say, vague. But now if you observe Kai Hong's book, there is something that is known as latency hiding technique. So in presence of multiple misses, your processor can serve better hits. Hits deto to tumhala. That capability is only with a better performing processors like Intel Core i7, i9, AMD's Ryzen. It is giving in presence of misses, non-blocking cache. The particular hits. Misses जरी present आहेत multiple, तो तुम्हाला hits देऊन serve करतो. Why it is happening? Not, throughput is not concerned whenever my host or CPU is there. That is concerned, yes. Reduce latency. So one of the best technique to hiding a latency part is nothing but your prefetching. Prefetch buffers. First optimization in Kai Hong's book. So what is prefetching? That is getting aggressively used in the particular era of Pentium onwards. Now also, so if you observe the difference between say AMD Ryzen's and Intel Core i7, you will get somewhat reverse result. Whatever I will be showing after our lunch part, you will be getting exactly reverse result. So why? So there are certain reasons. Along with that, that you are using smart prefetchers. Prefetching of what, sir? Data and instruction. So there, what I am doing, my host or CPU, I am trying to reduce the latency. That focus is on that part only. Hence, the type of cores whichever are getting used in processor or my host are known as latency oriented cores. Because the emphasis is on minimizing latency by doing tasks only. In contrast, in GPU, my particular job is not to deal with latency, because hardware whatever is designed, that will take care of the part. If any, my job or my focus is to increase throughput. That is nothing but the work done per unit time. Hence, when I say anything, likewise, we have 2 tracks again in that one. May I know? GPU शिकलाय ना? झालं का नाही GPU? नाही झाला का अजून? झालं? So how many tracks are there when we are concerned about the GPU? You might have learned only parallel programming track, how to write a C-based CUDA program, sir, using kernel, or you might have learned only OpenSSE based pragmas, how to utilize those pragmas for loop based parallelism, identifying and executing. Rather than that, what is the use? So we have 2 tracks mainly. One track that gives you system, the algorithmic, the programming way, parallelizing the applications. As I uttered, either C-based CUDA, OpenSSE, C-based CUDA or PyCUDA. So CUDA is a proprietary of NVIDIA. If you don't want to use it, you have a choice of OpenSSE. Okay? So likewise, the track will go one side. That is systems track or parallel programming or parallelizing application track. Another track is nothing but your, so these kind of cores, whenever we say, that are known as CUDA cores. Okay. So the cores that are getting utilized in this, that are known as CUDA cores. Second track is nothing but it allows you to utilize the GPU for AI ML DL kind of applications. You do something, sir, you create your model, you take your data set, either it is a tabular, pictorial, what you can say, motion picture, videos, and combinedly you put it on GPU and just start with certain number of epochs. Am I right? हे केलंय सर्वांनी, आता सगळं हेच चाललंय. Okay, so it is going on. So when it is so, then that kind of cores are known as tensor cores. CUDA cores, tensor cores. Because that is taking care of the particular kind of application design that is supported by AI, ML, DL kind of thing. And you can customize your model for number of epochs, how many folds, what is the capacity of data set, and so on. So why GPU only, sir? Sir, Colab Labs होतं किंवा मला पे करावं लागतं. I need to pay. Still my need is not getting satisfied. Why not just CPU? In meanwhile, 2018 to 21, almost the end of Corona, Intel was shouting, no need to use GPU. Our CPUs are sufficient. So we have CPUs of category gold class, silver class, and platinum class. Like for example, Xeon Gold class, 20 physical cores per core through hardware threads of execution, 40 logical CPUs. No need to use GPU. So why? The reason is that the particular performance is getting limited. The particular host is not capable to handle the kind of load that you are willing to execute using the particular part. That just allows you to make use of the concepts of AI, ML, DL. So we have 2 tracks. In this particular course, you might have learned how to write C-based CUDA code or OpenSSE, C-based OpenSSE code, and do some kind of parallelizing the particular kind of application or programs. Another track is this one. So whatever is there in context of perf and the practical, I will just continue after lunch. Okay? Is it fine, sir? Yes. So I meet 1:45. So we'll meet after lunch. Please continue.